Hello again and welcome. Today we're going to be looking at a Ruby Electronics DT9939. The CEM DT9939 is a 40,000 count meter. It has tri-displays. It's rated for IP67. These are wireless. They have an AC plus a DC mode. I purchased the Extech EX540 on the left. This is an equivalent meter to the CEM. So the reason I was interested in running a second one, first of all, I was hoping that if I bought another one, it may not have the same problems this one had. The big thing about this one is the cost. So this is teequipment.net, and we can see the Extech EX540 listed here. It has a sale price of $300. If you'd like the same meter with a NIS calibration, it costs $375. Just looking at Ruby's website, and here they list the same meter for $250, and you can see they have a sale price of $150. It's been independently certified to pass both the GS and TUV standards. We can see this one listed on eBay for $90. It has a $20 shipping cost with it. This one's up on Amazon, and this is listed by Ruby Electronics for $120, and with Prime this would be no shipping costs. So a little bit cheaper than what they offer it for on their website. If we look at some of the photos of this, in particular the box, we can see the meter is shown in yellow. If we look at this photo though, we can see it's actually marked CEM. So I don't know if they just get these at kind of random, that sometimes they're marked, sometimes they're not. So I think when you buy this, I'm not quite sure that you're guaranteed as far as what exact meter that you're going to be getting. Looking at the Ruby Electronics website, they have a frequently asked questions. You can see one of the common questions is, how can you afford to sell the products at such a low price? And they state here that we buy or import directly from manufacturers who are known to produce quality products for large international companies. We bypass importers, remarketers, distributors who often take huge profits for handling the goods. Therefore, we can afford to sell you quality products at a price much lower than retail. So again, I bought mine off of Amazon for $120. I bought that Extech from TE Equipment, and you can see it's a $300 meter. So that's a significant discount. The question is if this meter is the same as the Extech, maybe it's even better. And again, I had never ran the Extech EX540 across my transient generator because it was in such bad condition when I received it. You may remember the RF link didn't work. It was missing like the shield inside of the case. That meter didn't even turn on when I received it. So I've gone ahead and I've done quite a few repairs to the Extech, but now it's been modified so much, I'm afraid that it would really bias the test if I went ahead and transient tested it. So what I'm hoping to do with this new meter from Ruby Electronics is actually run it on the transient generator. This is the two cases that the meters were supplied in. You can see they're basically identical. The one on the left marked for Extech and the one on the right marked for CEM. Again, I really wasn't sure what this meter was going to be when I got it. And then when I opened it up, long and behold, this is what was supplied. You can see it's marked CEM DT9939. You can see the TUV and the GS marking on the front. You can see here it says, thank you for your business. If you like the products and services, please leave us positive feedback. Well, here you go. This is a big review. Warranty disclaimers. Yeah. Let's just see how this compares against the Extech. Of course, the two meters are basically identical, other than the color. See the RF link between the two. The Extech, of course, has been rebranded with the green. And again, this one was missing the two screws here. It only had the one, and of course this RF link didn't work when I received it. This one at least has the screws in it. Cabling appears to be the same. You can see the probes are just a little different. The Extech actually comes with the magnetic loop for the meter. This CEM meter does not. There's another difference. If we look at the thermocouple probe, this is the one that's included with the CEM. And this is the one that was supplied with the Extech, of course branded for Extech. Of course they each come with their own CD. Professional True RMS Industrial Digital Multimeter versus Extech, a FLIR company. See the manual for the two is slightly different. Surge protection, 8 kV peak. In this manual they never mention what the frequency is for the RF link. I know the Extech is running at 915 megahertz. So what's this here? CEM Machinery Industry Company test report. Model Ruby Electronics DT9939. You can see it's got a report number here and somebody has hand scratched in 3842. And it gives this serial number range. Manufacturer, it says Fluke. Calibrated by Lehman Long. Issue name Peng Zheng. Yeah, I'm not thinking that this goes with this meter. Let's have a look. So the serial number on this one is 1305, and you can see the sheet here is for up to 1304, so this meter is already outside of the serial numbers that the sheet is even talking about. So I'm not sure why they include this. If you're going to include a test report, I'd expect it to be for this specific meter. Extech must have them rebrand it with their own serial numbers, because they start out with an A1408. Actually, this CEM has a lot more digits to the serial number. You pop the rubber cover, you can see the Extech is marked for the FCC. This CEM meter is not. So let's go ahead, we'll take a look at the basic accuracy of this. We'll start with resistance. We'll just short out the leads. And this will be a 0.5 ohm. Real good. This is with a 1 ohm. Dead on. Turn the rel off. This will be a 50 ohm. Very good. 100 ohms. $1K. 10K. 100K. 1 meg. 10 meg. This will be diode check mode. This with a short. And with a single diode, 2 diodes, 3 diodes, and capacitance mode. So this will be 150 picofarads. Not that great. It's off about 40 picofarads. Let's try it with a 1000 picofarads. Looks pretty good. You can see it's still about 40 picofarads off. It's interesting because without the rel, you can see this thing's reading about 60 picofarads. So if we just hook it up, it's actually reading a little bit closer there, 170 picofarads. Of course, that's not the way you're going to use the meter. Let's see what it does here. This is a 0.1 microfarad. It's pretty good. And this will be a 1 microfarad. Looks pretty good. And this is with a 10 microfarad. Looks pretty good. Go ahead and test the temperature input. So this will be our K-type input. 71 degrees F, I could believe that. Or 21.6 degrees Celsius, so that seems fine. When I first purchased this EX540, I compared it with a second one, and I realized that this particular meter had a problem. Another member had contacted me who had the same series serial number, and lo and behold, his meter behaved the same as this one. One of the problems with the meter is when the inputs were shorted or floating or whatever, we would select the AC volt mode, and after about 20 seconds, this meter would clear out. And then what would happen is we could remove the inputs, and then this thing would start drifting all over the place. So I was assuming that was the RMS to DC converter. So let's go ahead and we'll turn these two meters on and let's just see what happens here. Now again, I've changed out the RMS to DC converter inside of this meter. So this meter is going to behave a little differently. I haven't gone back and realigned it since I've done that change. So again, we're past the 20-second mark, and you can see the readings on both meters are stable. This meter would have actually zeroed out at this point. You can see we're well over a minute now, and both meters are still reading the same values. Now I would expect, being past a minute, if I remove our short on both meters, and now I'm going to reinstall this, both of these should zero out. You can see the CEM meter is already zeroed. Of course, this had quite a bit of offset. And here goes the Extech starting to drift upwards. So both meters behaving very similar. So I'm definitely no longer seeing those same effects with this meter, but again, I've changed out the RMS to DC converter. So another problem that I had with the meter is if we shorted the inputs, then we'll select the AC volt mode again, and I'll enable the backlight. And you can see it's very stable. Do that with this one, and again, very stable. But let's go ahead and we'll let this thing sit for about a minute. It should be long enough. It's about a half a minute. Oh, there you go. You can see there's about 53, 54 millivolts being affected by this backlight. Let's just try that with the new meter. Doesn't appear to be as bad, but I saw a 33 millivolt in there. So yeah, I'm not sure what the reason for this is. I can tell you that my original Extech 540 doesn't have this effect. So changing out the RMS to DC converter in this meter had no effect with that. It's something to do with the newer revision meters that's causing this problem. I don't know what it is. I haven't dug into it any further. So currently I have all four of these meters attached to my fluke calibrator. On the left I have the Unity UT181A. On the right the Bryman BM869S. You can see the Extech is reading slightly closer than the CEM. Well within tolerance. And this is with 1 volt applied. Again, the Extech reading a little bit closer than the CEM meter. And this is with 1 millivolt applied. Let's just switch these down to the millivolt range. All of them look really good. This is with roughly a half a volt at 60 hertz being applied. You can see with the Extech and the CEM, they're not able to read the frequency. I think the amplitude is just too small for them. So again, this Extech, I've changed out the RMS to DC converter, and you can see it's about 2 millivolts low. Again, it hasn't been aligned, but not too bad. And this is with 5 volts being applied. Again, this is still at 60 hertz. Let's go ahead and we'll check the 3 dB point for the meter. So you can see I brought out the EEV blog rebranded Bryman BM235, and all 5 meters are attached to a 1 volt 60 hertz reference. This is in auto range right now, and you can see I can read 0.9 volts essentially. The rest of these meters much higher resolution. Now what's interesting is I paid $130 for this Bryman. Of course this one here, $120 with shipping and everything. So this meter is actually cheaper than this one. So just keep that in mind as I'm going through the tests here. So we'll go ahead and start increasing the frequency, and let's see how these roll off. So you can see I'm applying a roughly 700 hertz waveform now, and the BM235 is all the way down to 0.6 volts. The rest of them are roughly still 1 volt. This is at 2 kilohertz. Of course, the BM235 is now reading 0 volts. We're now at roughly 11 kilohertz, and you can see both the Extech and the CEM meter are close to their 3 dB point, while the BM869S and the 181A are still reading roughly 1 volt. Still not bad. I mean, 10 kilohertz is pretty respectable. Usually for a handheld meter like this, I'm not using them to do any kind of real high frequency work. I haven't bought a 9 volt transistor battery in quite some time. I've been using the batteries that were supplied with some of the meters that have damaged. You can see the battery indicator is starting to flicker on the BM869S. So we'll have to go ahead and change that thing out pretty soon. So right now I'm applying a 1 kilohertz waveform to all 5 meters. Let's just go ahead and increase that, and let's just see what the upper end is for this CEM meter. So you can see I'm applying 100 kilohertz right now, and this is the rollover point for the BM235. See, right now it's already rolled over, but the rest of the meter is not having a problem with this. This is with a 10 megahertz signal, and you can see the BM869S is no longer able to read it. And this is because this meter is not as sensitive as these. So if I were able to boost the input signal to the meter, it would actually be able to read up past about 20 megahertz. You can see we're at roughly 22 megahertz, and this is roughly the upper limit for these 3 meters. Again, if I just turn this up a little higher, we can see here that the UT181 is starting to have some problems now. It's pretty good. So the CEM meter is all the way up to 27 megahertz. Our Extech meter now is starting to fold back. This is at 28 megahertz now, and you can see the CEM meter is also having a problem with this as well. This is looking at the bar graph feature. Of course, the BM235 doesn't support this. This is with a 0.1 hertz triangle wave being applied. You can see how smooth 181A and the BM869S are compared to these. Again, I'm not sure why they would put the feature on these 2 meters. This is basically useless. You can see I've selected the microamp range, and all 5 meters are placed in series. I'm currently supplying 157 microamps to each meter. You can see they're all relatively close, certainly within 1 microamp of each other. And this is with all 5 meters in their milliamp ranges. You can see I'm applying roughly a 345 milliamp signal. You can see all 5 meters are now in their amps range, and I'm supplying roughly 5 amps through them. So for this next test, all 5 meters in the oscilloscope are hooked up to my ARB. You can see I'm currently applying a 1.4 volt 60 hertz waveform. Looks like the LaCroix is reading roughly 1.41. This is with a 4 volt peak to peak triangle wave applied, and you can see all 5 meters are still reading roughly the same value. This is with a sine wave that's being AM modulated with the fifth harmonic. The modulation depth is roughly 20%. And again, this is with a sine wave that's being amplitude modulated with the 10th harmonic with a depth of 50%. This is a waveform from EX540, and we can see this is basically a flat top sine wave. This is with our Fourier square wave, and the LaCroix is reading roughly 1.5 volts. Looks like the LaCroix is reading roughly 620 millivolts. In all 5 meters, roughly the same value. So looking at the RMS conversion for the CEM, it looks just fine. So again, on the Extech, because I've changed out the RMS to DC converter and not realigned it, you can see this is off just a little bit. Currently I'm applying about a 37.6 volt sine wave to all 5 meters. What I'm going to do is rectify this. So again, this will be a full wave rectified signal. And we can see now all the meters are reading roughly 16.5 volts. This is with all the meters set to their AC plus DC mode. See the Bryman reading roughly 16.5 volts AC or 37.6 volts AC plus DC. Again, I'll reapply the sine wave, and this value should basically not change, except I've got the drop of the diodes that you'd have to consider. Now, of course, the little Bryman doesn't have the ability to read this directly, so we'd have to select and read the DC value and read the AC value, and of course then we'd have to calculate that. So again, you just take and square those two numbers, add them, and take the square root to get your AC plus DC value. But again, both the Extech, the CEM, this Bryman, and the Unity all support that feature. I have a few other ones that do that as well. So here you can see the receiver that came with the CEM meter. It's just a small antenna that's connected up to my signal hound. This is looking at the BB60C. You can see the center frequency right now is set for 915 megahertz. This is looking at the Extech meter talking to the CEM adapter. I'll go ahead and turn off the Extech, and let's turn on the CEM meter. You can see they're both using the same frequency. I looked at both software packages. It appears that all they did for Extech was relabel the menu from a DT9939 to the EX540. Currently you can see I'm logging the data from the CEM meter. This is with a 1 volt peak sine wave. I recently did a video where I was using the BB60C to decode the data off of the Extech EX540. You can see I've cleaned that software up quite a bit. This is looking at the raw IQ data. This is the BB60C settings, and this is the serial data link settings. Here we can see the data that's being displayed on the CEM meter is updated quite a bit faster than what's being transmitted. You can see I have the antenna in my right hand, and as I pull this away from the meter, we won't pick it up anymore. It's just where I've set the thresholds. So I bring the antenna back up close by the meter. Again, we start receiving the data. So it's good to know that this meter is using the same frequency as the Extech. Currently I have all 3 meters attached in parallel, and they're connected to my high voltage power supply. You can see we're at 981 volts. This is the upper limit of my power supply. You can see I'm putting out roughly 540 volts at 60 hertz. It's interesting, the Extech meter is actually reading this as 120. And right now I have a 10.6 volt DC offset. What I'm going to do is adjust this a little bit. Let's just see what effect that has on our AC value. So this is a 300 volt offset. And this is minus 353 volts offset. This is in AC plus DC mode. You can see the Extech's reading 120 hertz versus the CEM reading 60 Hertz. All three meters reading roughly 542 volts or so. So when I was looking at the frequency counter functions of these various meters, I had mentioned that my Bryman BM869S could actually run in excess of 10 megahertz and closer to about 20 megahertz. And the reason I said that it wasn't able to read up that high was because this meter isn't as sensitive as the other ones are. And I suspect the reason that this thing failed at about 28 megahertz is the same reason. So you can see I have it now connected in series with a power amplifier. This is just a load, and this load has an attenuator built into it, so I have a monitor tap that's going back to the oscilloscope. Currently you can see I'm putting out roughly 5 megahertz. So let's go ahead now and we'll increase this frequency and see where this thing falls off at. So this is already past where it was having troubles on the RF generator. You can see it just changed ranges. We're at 40 megahertz now. See, we're starting to get into the area where the amplifier is working good. So currently I'm putting out 84.24 megahertz on the RF generator. See, the meter is very accurate. Not a lot of resolution, but it's accurate. So currently I'm running the amplifier right at its peak point, and the synthesizer is set for 154.02 megahertz. And you can see the meter is not having any trouble with this. So I think it's a question of just getting enough amplitude into the meter. You can see 154 megahertz. This is off our LaCroix. 154 megahertz. Again, this basically connected in series with this power amplifier. It's pretty impressive. Alright, so we're going to go ahead and take this thing apart. This is one of the things I don't like about this meter. You can see how difficult it is to get these open. It's got a golden power battery in here, but look at how this is held in here. See, the other meters, the original ones, are not made like this. These actually have a 9-volt battery clip in them. So you got your little 9-volt cable. Actually, I like this a little better. These you have to disconnect the battery and push the cable through the hole to be able to take the cover off. If that's all they've changed, this will be a great deal. Check this out. SEBA 10 amp, 1000 volt fuses. You can see the 3 MOVs here. A bit of plastic residue. This will have the 3 MOVs on the bottom as well. I don't know if this will show up on the camera, but this is the original ES636 that was included with my first Extech EX540. This meter came with something completely different, and again, I've changed out that RMS to DC converter, and it definitely had an impact on how this meter behaved. So it looks like they've gone back to the original ES part. Boy, the soldering looks real good on it. You can see down here is a bit of a blob. That's a lot of thermal mass to try to solder. You can see over here there's a lot of flux residue. It's actually splattered up onto the case up here, but it's not all dented up like the other one. As a matter of fact, yeah, you may remember on this meter that shield was missing off of the back cover. I wonder if TE Equipment just didn't sell this to somebody who took this apart for a review and then had resold it as a new meter. This just looks night and day different between this and this meter. I'll go ahead and remove the circuit board. Again, it looks very good. I don't think we're going to pop the can or the LCD. You've seen the other meter apart. It looks good. I'd say this thing is definitely worthy of running. I'm not going to change anything with this. So yeah, let me just go ahead and we'll reassemble and we'll start the transient testing. The only thing I noticed here while I was putting this thing back together, this one actually had all 4 star washers. Again, this meter was actually missing one. It just looks more and more like this meter was sold by TE Equipment and then it was returned after somebody had tore it apart. They don't put any kind of a tamper-proof seal on them. I know my Bryman actually had something like that with it. You know, at least then they would know if customers were taking them apart. And that maybe they shouldn't resell them, but you know, and again, this meter didn't even turn on when I received it. There was a problem with a switch that I had to repair. One of the advantages to owning these meters is they do meet the IP67 right here. IP67 waterproof. So that might be something that's important to you. This is the UT90A. I'm thinking to run some waterproof tests on it. Reading roughly 0.3 ohms. Looks pretty good. Ooh. Maybe make a snowball out of her. What do you think? Still working. Well, she landed a ways down there. Let me go fetch her. Seems to be working okay. Oop. Let's try some water immersion test with her. Yeah, water's got to be cold. Oh, still reading continuity just fine. Maybe we didn't go deep enough. You can see it's still working. You can see it staying running. Let's just try the continuity test underwater. She's a little slow on the release, but still working. As you can see, it still has some water in here. So we got the leads attached, and we're in the 20 mega ohm range. And just touch this with our fingers. About 2 mega ohms. Here's your IP rated meter, but that's not how we test things here. This is how we test them. For this first test, we have the DT9939 attached to our transient generator, and we're just going to enable the 220 volt rectified AC signal. You can see it's displaying 217 volts, and we'll just work our way through the different settings. I don't know what that error was. Did you see the EE? It's definitely reading the AC and the DC voltages still correctly. I'll go ahead and functional test it. Alright, so the meter checks out just fine. I don't know why it went into the error mode. I thought for sure maybe the temperature inputs might have been damaged, but does not appear to be the case. So next up is the infamous grill starter. And again, we'll be applying 5 each of both the positive and negative transient with each mode of the meter. Alright, let me go ahead and functional test this. Alright, so passed the ESD test just fine. Again, if you have questions or concern about this particular test, I know this has taken out a lot of Unity meters. I did post a video where I characterized this and compared it against the IEC standards. Before we go any further, I had forgot to mention I performed a continuity test on this particular meter, and you can see it's quite slow. This meter reads a short at 27 ohms and an open at 28 ohms, so it has virtually no hysteresis for the continuity test. With a 50% duty cycle waveform, it can read up to 1.8 hertz. The minimum pulse width that it can detect is 100 milliseconds. The open circuit voltage is 1.257 volts, and the short circuit current is 406.9 microamps. This is our test setup. You can see the high voltage probe attached to our oscilloscope. Scope currently is set for 500 volts per division. You can see we are roughly 1000 volts. Alright, we'll be running both positive and negative transients, 5 pulses per each mode of the meter. This will be 1000 volts peak, a 100 microsecond full width half height, and a 2 ohm source impedance. Okay, the CEM meter checks out just fine. Meters that failed the 220 volt rectified signal are the TechPower TP40, the Unity UT20B, the TPI Summit TPI194-2, and the Maztec MS8211. Meters that failed the ESD testing are the Unity UT61D, the UT61E, the Extech EX540, the Vichy VC99, the Unity UT181. Meters that have failed the 1 kV transient we just performed are the BK Precision 2705B, the Circuit Test DMR 6550, the UTL DM2, the Southwire 12070T, and the Innova 3320. So So I've reset our transient generator. You can see the scope is still set for 500 volts per division. We are putting out roughly 1.5 kV. And again, this will be a 2 ohm source, positive and negative transients in all modes of the meter. Alright, the meter passed that just fine. Meters that had failed that test were the Unity UT90A, but that was after it had been repaired from our initial round of testing. The Amprobe AM530. Oh, I'd gotten this wrong. The TechPower TP40 failed this test. It was the TechPower TP2844 that had failed the rectified AC test. Other meters that had failed the 1.5 kV transient are the Fluke 87V, the Victor VC921, and the Maztec MS8211D. This is still 500 volts per division, or 4 divisions up, or 2 kV. Again, 5 transients each, positive and negative. 2 ohm source impedance, 2 kV. 100 microsecond full width half height. Alright, that was the 2 kV transient, and the meter is just fine. So only one meter had failed that test, and that was the Klein MM2000. At this point it looks like 20 out of 35 meters I've tested have failed. So this meter is actually in the high percentile already. Okay, the transient generator has been set up for 2.5 kV. And this will be a 2 ohm source, 100 microsecond full width half height. Alright, so unfortunately it looks like we've damaged the meter. So it turns on just fine. There's a little bit of leakage in the millivolt range is the first thing I noticed, so looks like it's reading about 500 microvolts low. And you can see in resistance it's reading 2.4 k ohms. And then diode check 1.7 volts. And it's also reading 24 degrees Celsius. So let's go ahead and we'll take this thing apart and have a look and see if we can figure out what got damaged. Alright, so you can see I've completely dismantled the meter. Again, on that last Extech that I had purchased, they had scrubbed off the part number. So when I went back to my original one, they actually had the part number on it, and that's how I got it. This is what I found so far. This pair of transistors, Q12 and Q11, are still intact. Q9, Q10 have failed. Q13, Q14 have failed. And Q4 and Q, it looks like 21. These have all been damaged. So I'm hoping that the clamps here have saved the chips. So the next step is to solder in all new parts, and then we'll check it out. Alright, let's reassemble it and we'll see if it works. Again, these are the transistors that had failed. These are at 2904. I think they use those for the low leakage currents. This is just a back-to-back clamp. And again, the transistors that had actually failed are this one, this one, this one, this one, this one, and this one. These two are still the originals. So if we look at this design, essentially we have three parallel circuits. There's a 1K ohm resistor, it's in series with a PTC, and then there's two MOVs that are placed in series, and then that goes back to ground, and then there are two back-to-back 2904 transistors that act as our high-speed clamp, and then this goes off to our input. Obviously these are our 1K ohm resistors, and the PTCs I've got it drawn backwards here, but the PTCs are underneath the circuit board. And then here are our three MOVs, and then the other MOVs are underneath the board. And then these 6 transistors that we just blew are the 6 that I'm showing here, I believe. So I traced this out a little bit. If we look at the 8 transistors that are located here, if it's in millivolts range, this resistor attaches up to this transistor, so this was the clamp for the millivolt range. This resistor is used for the ohms range, and then that goes up to this transistor here once the selector switch is in that mode. So yeah, I believe that this is what they've done. There's probably some ways that you could correct this, but you know, to be honest, this thing is such a mess already, especially with this ground trace here. You know, this is the only place the meter gets the ground. They route this clear up to this location here. You know, the MOVs and everything are located here, so that means this transient's got to travel all the way up along the edge of the board here. So I mean, just on this alone, I don't like the design of the board. But yeah, I probably could improve it. I just don't know if it's worth the effort. And to be honest, I think what I want to do is just keep this meter as close as I can to the factory conditions, and I'll use it for demonstrations. Currently this is with a 10 mega ohm, 1 meg, 100K, 10K, 1K, 100 ohms, 50 ohms, rel, and this will be a 0.5 ohm. So it looks like the resistance modes work. Let's try capacitance. This will be diode check. Series with a short. Yep. Yep. So that's fine. Continuity test. That's fine. And let's see, this is a 1000 picofarads. Looks good. And a 0.1 microfarad. That looks fine. Degree C now should be an open. And this is with the thermocouple attached. That looks fine. Starting on the far left, we have the Unity UT61E. This meter costs $50 and is a resolution of 20,000 counts. It doesn't have a temperature input or a backlight. It's also the least robust meter of the entire group. It's also second to the worst temperature drift out of all the meters that I've ever tested. To the right of that, we have the Amprobe AM530. This meter was supplied by 5KY. This meter costs $80. It has a resolution of 4,000 counts. It's also true RMS, and it has a temperature input as well. Also has a non-contact voltage detection. Next we have the Fluke 107. This meter costs $110. It's also 6,000 count, and it's the only meter out of this entire group that is not true RMS. This exact meter was exposed to, I think, a 15,000 volt 100 microsecond full width half height pulse with a 2 ohm source before I finally damaged it. Again, I was able to repair the meter. It still works today. Next to this we have the CEM DT9939 that we just got through looking at. This meter cost $120. It has a resolution of 40,000 counts. It also has a temperature input, and some of the big features with this is it has a 4 to 20 milliamp conversion input, and it also has AC plus DC. It's also a tri-display, and it's IP67 rated. Another thing about this meter is it has a wireless data link back to the PC. The UT61E can also record data on the PC using a USB port. Next we have the EEV blog rebranded Brahmin BM235. This meter costs $130 and has a resolution of 6,000 counts. The meter also has a temperature input. One of the things about this meter and the Fluke 115 and the Hioki next to it, these all have a fairly low AC frequency response. Now that little Brahmin I've actually tested to some fairly high levels and I've never damaged it. The Fluke 115, the same way, I've actually ran that meter up quite high and I've never damaged it at all. That meter cost $132 and is 6,000 counts as well. To the right of that we have the Hioki DT4252, and that meter costs $150 and that's also 6,000 counts. I think that Hioki and the Fluke were meant to be in competition with each other. They both have basically the same set of features. Personally, I would take that little BM235 out of either one of those meters. Next I have the Brahmin BM869S. This is the actual meter that I use. This meter costs $230 without the data link. It has a resolution of 50,000 counts and it has dual temperature sensor inputs. It's also an AC plus DC meter, and it's also a multi-display. Next to that we have the TPI 194-2, and this meter costs $250. It's also 50,000 counts and has AC plus DC support as well. This meter actually has some very nice features, but it's not robust at all. That meter got damaged from the ESD testing. To the right of that we have the Extech EX540. This meter has had nothing but problems. Right from the box as it was shipped to me, the meter didn't work. While that meter and the CEM are functionally basically the same meter, for whatever reason the Extech, they had changed the RMS to DC converter. That was definitely causing me some problems. I'm not sure if that Extech is a little newer or if the CEM is. My original Extech actually worked a lot better. The Extech costs $300 and has a resolution of 40,000 counts. Finally, to the far right, we have the Unity UT181. This is the most expensive handheld meter I have. It has a resolution of 60,000 counts. It also has dual temperatures like the Brahmin, and it supports AC plus DC. It also does graphing. So a very nice meter, except again, this meter failed ESD testing. It was not very robust at all. I was able to repair it. You could see where I made that meter quite a bit more robust by changing the circuit board layout, but that's not something that you're going to want to be doing. So unfortunately, if you were to go out and buy one of those meters, you're just going to have to live with the fact that it's just not a very robust meter. So again, for my own use, I would still take that BM869S. That's still my favorite meter out of this group. You know, that CEM meter for $120, I can tell you I would pick that meter over pretty much all three of these. I would also take it over that TPI. I'd certainly take it over the Extech. This for $120 is a very nice meter. It just has a lot going for it with its tri-display. It's very high resolution. The thing I don't like about it, and I haven't verified this against this meter, but I know this one has the highest temperature drift of all the meters that I looked at. Well, I think that's going to be it for this review. I hope you enjoyed the video. I'd like to welcome all you new subscribers. Until the next meter. Later.